All right, once again, welcome everybody to the 2020 Collegeville Workshop on Scientific Software. I'm looking forward to the conversation we're going to have over the next few days and participation on Slack and other forums. Hopefully this will be a good event for everybody. And we'll all walk away knowing a few more people, at least virtually, and knowing a bit more about the art and craft of scientific software. Before we go further, I'd like to thank our sponsors. Both Intel Corporation and the MathWorks Incorporated have provided funds, and that money has gone directly to support the student staff who are helping out with this meeting. We have 5 students who are working with us. If you're interested, you can go meet them virtually on the YouTube playlist on the Collegeville channel. There's a brief video showing each of them. And so our thanks to both Intel and the MathWorks for their support. So I wanted to give a little bit of an overview of the purpose of the meeting. Although, generally speaking, there are quite a few meetings about software engineering and software productivity. What I wanted to get out of this meeting was to bring academia, industry, and labs closer together. And certainly there are already connections, and what we're trying to do here is reinforce existing interactions, and also to create some new ones and come to a deeper understanding of the characterization of these communities and what impediments and what opportunities lie that allow or make harder interaction between these communities, because in many ways we're all focusing on very similar challenges. We all want to advance science. We all want to get our job done. We all want to build up the next generation of people who work in this area and generally learn from each other. And there are lots of opportunities for doing that. And so that's the purpose of this meeting. The main purpose is to build that community, build a deeper understanding within and across communities. And so that's our hope. That was our hope in creating the videos, collecting the white papers and posters and tea time themes, and for the next few days. And then after the meeting as well, we'll keep this Slack workspace going. I've created already a new Slack workspace for the 2021 workshop and hope that people will join that before we put our minds to other things at the end of the week. I do want to mention our code of conduct for the meeting, and we hope that everyone will respect what's stated here and the extensions of this to other hopefully common sense approaches to interacting with each other. We all are very passionate about what we do. And that's a great thing, and let's keep the conversation respectful. Just a brief overview of the agenda each day. So we're starting our opening remarks right now, and then every morning we'll start at 10 a.m. Central U.S. Standard or Daylight Savings Time. If you are want to make sure you get the right time zone translation, each of these has a calendar invite that you can click on, and the file should load and appear in your calendar tool and give you the option to save it. And then the time zone translation should occur correctly. We're doing everything using Zoom, courtesy of the College of St. Benedict and St. John's University here in central Minnesota, who are hosting the Zoom accounts that we are using, and also of which myself, I'm scientist in residence, and the students are enrolled at these 2 colleges and universities. So the panels will be single session, and we will have 6 panelists for each panel. We're going to start each panel with a brief introduction of all the panelists, allowing them to say a little bit about who they are, their thoughts on the topic of the day, and then we'll open it up for Q&A. After that, we will have a discussion. We'll start the discussion with a single Zoom session. So please try to be prompt in signing in. The Zoom link is already in the Collegeville main page Google Doc, so you could look for it there. And then about 12:35, we'll click the random button and on the breakout rooms and try to get 6 to 8 people. I'm not sure how many people are going to show up for the session, but we'll try to keep the number of people between 6 and 8, and then allow discussion to occur over that 90-minute span of time, or until the group runs out of things to say. We'll give you a little bit more instructions for that at the end. The tea time and poster sessions, they will be separate for each of the sessions. So for each poster, there will be a Zoom link. For each tea time topic, there will be a Zoom link. And so you're free to come and go as you like to those. There's roughly 6 of those per session. So hopefully you can get to see at least a few of them. And we're trying to emulate in a way how, say, one of these informal sessions might be in real life. And we'll see how it goes. In part, this is an experiment, at least for me. I haven't done something like this much in the past, and so hopefully it'll go well. And as I said, the Collegeville main page is available as a Google Doc, and I created a tiny URL link that you can find here at Collegeville 2020. All right, so I also wanted to highlight that we have roughly 29 videos on the Collegeville YouTube channel. 9 of them are interviews with a variety of community members, some junior, some senior, from all parts of the community. We also have 10 group discussions where this was based in particular on white paper contributions that had similar themes from different groups. And we thought rather than having each of them give a presentation, we would have a discussion around that particular topic. And those are some of my favorite videos because they elicit more and create synergies between the groups who have contributed things. And then we have 10 presentations from the white papers, which I have found just very high quality. So I think our video content is quite attractive to view now in between discussions and in the future. And please feel free. We're doing still some more cleanup on them. This is our first time doing this kind of stuff. So we're putting in more metadata, but hopefully it'll be a nice collection of resources to anybody who wants them. And then we also have the 33 white papers, which provided really in a way the foundation for the content for the meeting. And most do have some related video content. We encourage use of Slack during the meeting, and especially during panels and breaks. What we're going to try to do, if we can, is we'd like to keep the Zoom chat focused on the Q&A, just to keep the kind of mixing of things down. Again, this is an experiment. We'll see how it goes. If you can keep the chat associated with the stream of conversation, so you hear something in the panel that you really like, or you want to add to it, or provide a resource, try to do that in the Slack channel for day 1, if you can. If you have a question for the panelists, then please put that into the Zoom chat, and we will then take those as the questions when we get to that phase of the panel. We will have, if you desire, and we encourage this, if you would voice your own question, we'll type it briefly into the, sorry, I have instructions here. Oh, okay, okay, just making sure. Voice your question, put it briefly into the chat, the Zoom chat, and then we'll ask you if you are interested in stating the question yourself verbally out loud, and then allow the panelists to respond to what you say. Okay. Any questions before we get started? Okay, let me just take a look at the chat here quickly. All right, I don't see anything so far, so that's a good sign, I think. All right, let's keep going then. All right, and I've checked to make sure that all of our panelists showed up in the participant list. Wonderful, thank you all for coming. I'll be the moderator today, and we have with us Rick Arthur from GE, Sunita Chandrasekaran from the University of Delaware, Fondue from the University of Texas, Finkel from Argonne, Todd Gamblin from Livermore, and Theresa Windus from Iowa State. Just an excellent panel. I'm really looking forward to hearing their introductory remarks and getting the Q&A going. So without further ado, Rick, are you up and ready to speak to your slide?
Good morning, everyone.
Morning.
So, and I may, as the first speaker, get this a little bit skewed to things, but as an industry participant and using the template that Mike had provided, I actually kind of tipped towards an anti-pattern definition rather than a definition here. So being from industry, I think we have other kinds of challenges that hopefully I'll illustrate in the bullets below. My background is in software systems engineering, and I've run groups in advanced computing. I do a lot of the interfacing with people outside of GE. So this kind of event is fantastic for us to learn and try to contribute and provide, maybe a perspective that's a little different than the labs and industry as an industrial user, not as a tech vendor like Intel or IBM. So taking the definition is the opposite, right? We want to avoid waste, yet be able to take advantage of opportunities that present themselves. And so the productivity challenge is avoiding the roadblocks. So in a lot of ways, as a leader or a mentor, you want to try to be the bulldozer or the tactical airstrike that comes in and gets things out of the way of the people who are just trying to do their job and be naturally productive. So there's a level of trust in that, and maybe more of the obstacles are constructs. So just as Agile has its deadly sins, the industrial manufacturing process of Lean enumerates these 7 deadly sins. And I'll skip the first 4 categories in there. I combined some to get to the ones in the larger font. So one of the challenges from industry is really the lack of time and concern over risk of adopting external components. So the E4S is out of the Exascale project is very exciting to us, but getting people to shift from legacy approaches, especially as these have been qualified and built trust over time, or the tendency to say, I need to control this, or I don't trust what's outside, and building yet another piece of legacy. Because we do work in a high consequence world, safety critical applications in medical imaging and aircraft engines, power grid, we are under regulatory certification, and nobody ever wants to sign off on a relaxation. So we conservatively interpret the standard, and then there's a hiccup, and so they add a further restriction, and it can monotonically grow with no real counterforce to simplify this over time, because it's all risk, and nobody wants to be the person who's now responsible for saying, oh, we don't need to do that anymore. I do think there are opportunities, though, to rethink regulation through the digital data and modeling and simulation medium, where you can look at it as a collaboration between the regulator and the supplier, where you both want to have something that is efficacious and safe, et cetera, rather than it being about audits and tests and high-risk events. It can be more of a continuous and agreed upon engagement between the two parties. So to the point of being the bulldozer or the airstrike and unleashing more productivity or knocking down the obstacles, I've used this UFODW form. The critical piece here is that, especially as you're managing remote teams or have a distributed development effort, you really need to expose any of these detriments that are getting in the way of productivity. Who's waiting on something that we could easily remedy? Who has some upcoming obligations or requests from another project? Who's maybe unclear about the prioritization, and you want to stimulate a dialogue to get to clarity for decision-making, clarity for what actions to take, focus for the teams that you now are entrusting to be as productive as they can themselves, and then the requisite empowerment for them to do so, which includes confidence rather than introducing conservatism and defensive behaviors in that process. So we'll have this table to reference, and that's how I laid the groundwork in my take.
Thank you very much, Rick. That's a great way to start us off. Sunita, you're next. Do you want to say a little bit about yourself and go through your starting point?
Sure. Thank you, Mike, and the rest of the organization committee for putting this together. It almost feels like we are in the same room, but I guess this is how far we can go. So thank you, everybody, for joining. Rick, you wonderfully set the stage. So I'm going to probably touch upon a few other things that you mentioned. I'm Sunita Chandrasekaran. I'm from the University of Delaware. I'm an assistant professor there, and I run a team of graduate, undergraduate students, and fun working with them and repeatedly telling them the, different challenges of software productivity and how they could, work through their software packages and make it usable. So I jotted down some points, and the pre-recorded video, it probably talks more to this. So, do definitely check that out when you get some time, because I'm probably touching base on several case studies to the points that I've mentioned in this slide. So the very first question that I, tend to ask my students quite often is, you have created a wonderful package, and one day you will graduate and go. We all want the students to graduate and go conquer the world. And when they do that, who is going to use your package and how, right? How is somebody going to pick up the package and move on? So there are several aspects to putting together a very good software that somebody else jumps in and picks up from where you left. At the same time, there are many challenges to do this in a systematic way. So some of the challenges that we have observed as part of my team, and I have 8 active projects with NSF, DOE, NVIDIA, NCAR, Nemours Hospital on HPC machine learning, and there are a lot of tiny little projects, wondering if they will morph into something bigger tomorrow. But the stuff that I've listed is quite common to all the projects. When we look at a car project, Oak Ridge, a car project in preparation for Frontier, we look at pick on GPU and try to see, okay, the algorithm expressed in the code, it's for the application. Is it well expressed for the parallel hardware architecture underneath? Maybe not. Most of the case it is not. And legacy applications tend to focus on a CPU-based algorithm while we are looking at a GPU hardware architecture. So how do you work from the algorithm standpoint to make the code compatible for hardware architectures? A. B. Classic problem. We have this in our next generation sequence alignment problem, where we look at a lot of related work and we want to evaluate our work against a solid, research paper, a work which is presented in a research paper, and we look at the GitHub and we want to reproduce their work, there are issues. And I'm sure all of you on the call can relate to this. There are issues because lack of documentation, lack of proper README files. And then we tend to compare to what they have written in the research paper, and we don't get to reproduce their work because of lack of data set or lack of steps or what have you. And something else that I tend to tell my students a gazillion times is you sit with a 5,000 lines of code, you're never going to figure out where the bug is, right? So make it modular and break it into so many different pieces. And when they do that, they do nail the problem, because to debug, you need to find the problem. Another issue we have had in our NCAR project is we ran into this bug in December. We are still fixing it. And why did we do that? Because we did not adopt good software engineering practices. So fault is on us. We did not test it, every step of the way, or we missed the steps. We didn't build a regression test from the get-go. Now we have Jupyter notebooks, and we are running every, version control against the regression test. So you want to do that with a bigger piece of code, but especially when you have computational scientists and domain scientists working together, because you want to make sure you don't lose accuracy, sensitivity, kind of important domain metrics. So don't use version control, you have a major issue. So basically the solutions have been regression testing, Jupyter notebooks, modular workflow, and automating several pieces of the workflow. This is something we're trying to do with the ECP validation verification testing project for OpenMP offloading, where we initially wrote a chunk of tests, right? But there is a workflow that you can create to make it, to automate several pieces of it. Documentation is intentionally in caps. We get so overwhelmed and so engrossed in writing software that we forget a document, we forget a comment, and it's going to be a tough job for somebody else chiming in and picking it up. Reporting bugs via ticket system. For car project, for example, we have a deadline to meet, we ping the vendors, but we also need to file the ticket system, tickets via the system. Then often, when you report a compiler bug, vendors are going to ask you for a workaround. It's easier to find the bug when you give them a workaround than dumping, 10,000 lines of your original code. So easier way to attack the problem. So those are some of the stories going on in my group. Thank you, Mike.
Thank you, Sunita. That was a very nice introduction to academic world. Fandu, and I hope I'm saying your name as you tend to say it. You're up next.
Yes, I go by Fan. Thanks, Mike. Very glad to be here because, so I'm Fan. I am currently doing my research on scientific software work. Most of the time with the James always at the University of Texas at Austin. James around here today as well. He's very enthusiastic about software. And we actually have some ongoing engineering efforts trying to facilitate scientific software work. So for example, currently we are mining mentions of software in scientific literature and develop some information retrieval functionalities on top of that. And actually we're going to host a poster session this afternoon as well. So if you have some ideas that you want to share and actually user requirements, let us know what you really need, and welcome to drop by our poster session. So for today's theme of the panel, developer productivity definition and challenges. So before we talk about the productivity of scientific software developers, I really want to discuss first what constitutes the development work that needed to be done. And based on our prior interview findings with RSE's research software engineers and scientific researcher developers, we learned about how they work with software components. And we want to propose an ecosystem perspective to looking at the scientific software work and projects. And of course, echoing Rick, we are very excited by E4S that Mike has some work, and perhaps, I don't know, maybe some panelists and participants in today's workshop that have actively engaged with this effort. But I want to discuss everyone's software work. When you're building on your own software component, so unavoidably you pick up other software components and your software stack will be used by others. But everyone, so no software is an island, but everyone perhaps working on their own software stack, their own software assembly. And it's hard for every developer to have the whole picture of how my component is interconnected with others and how the interconnected components, the upward and downward dependencies are making changes, how they update themselves, how they fix their bugs. And when this change happens, what impact will it have on my software stack? And when the change happens to my own software stack, how would that impact others? So we really want to propose with this relational view of scientific software components. So we think this kind of work, because it's less visible and less aware of, perhaps. So most of them are kind of fail to be seen and fail to be done, but it is important because thinking about the overall structure, the dependency structure of scientific components that floating around everywhere, that might lead to future dependency hole or really reduces the sustainability. So when we are thinking about the sustainability of the whole scientific software space, it is all related. We have to account for others as well. So we would like to propose that there are three kinds of ecosystem work once we adopt this view. There are three types of work that needed to be done within. And the first category of ecosystem work is the work of sensing. How do you know that and how much you have done for knowing how your software is used with other components? And this kind of speaks to first the structure of the dependency structure within which your software component is used, and also what are the complements of your software in different use contexts and use scenarios. And the second category of work is the adaptation work. That is once the interconnected software component changed, there's some change to the nearby ecosystem in relation to your own software component, and how do you adapt to that environmental change? And it is important that all the interconnected software components to change in sort of coordinated pace, because we need to. So this speaks to the third category of ecosystem work, that is the staying in sync with the nearby ecosystem. So all the interconnected software components kind of update and change themselves in a well-paced manner. So just leads to less, messy, uncoordinated work going on that increasing the risk of scientific software. And of course, we would like to hear more from your first-hand experience, because we have many brilliant scientific software developers here in this workshop, and the scientific software work is constantly evolving. So for example, with the application, the increasing number of machine learning application, scientific software work becomes more complex, and it might be hard in the machine learning development context to keep a very neat modular workflow. So what are the real challenges you are having now? We would like to hear about this, and how do scientific software projects account for these categories of ecosystem work? And if they're less visible and less attended to, how do we motivate such kind of work? Are there metrics that we can use to kind of orient such work? And I draw on the example of software publications, which really incentivizes efficiently that the formal release of scientific software, I think. However, it might not incentivize the maintainability that built in your software components. Maybe when you're chasing the publication, whether you have the time to really build the interoperability for future contributors to your software. And when I talk about maintenance, I really want to make the distinction between the maintenance inherently needed in the daily development work and the maintenance work additionally involved. Once you take on to this ecosystem perspective, how you account for all your dependencies and nearby ecosystems and the potential risks, changes, and maintenance costs that involve. So I think that's what I want to speak out now.
Thank you very much, Fan. Yeah, those are great questions, and the answers are challenging. So thank you. Next, we have Hal Finkel. You want to introduce yourself a bit and do your intro? Thank you.
Sure. I don't know, can you? I don't know if you can see me now,
Yeah,
but
yeah, we can.
Okay, great. So, hi, I'm Hal Finkel. I lead our compiler technology and programming languages team at Argonne National Laboratory's Leadership Computing Facility, and I'm going to talk to you just for a few minutes about the way that we try to view productivity. And I think, one thing I'll say up front is that this is a important topic that has been discussed a lot, of course. And one reason that this has come up a lot is that as we look at how we invest in technologies to improve productivity, this question comes up, well, okay, how do you measure that? Right? How do you tell whether you've really created something that improves productivity or not? And I think that the really key thing here is that you have to have a very broad view of productivity, because the software lifecycle has lots of different components to it. And you can improve productivity in one or many of those parts of the software lifecycle and have a good return on that investment. So when I look at software productivity and how you define it, I view it very much in a kind of time to solution sense. So if from the point in time when you start planning a piece of software all the way through the kind of end of life, is some piece of technology, some technique, some advancement, does it help decrease the number of person hours necessary in order to accomplish any of the tasks in that whole life cycle? And I think that these are and they're really important challenges and also opportunities in all of these places. So I wrote a white paper, recorded a video that talks about a lot of these things in more detail. Let me just quickly try and address what I think are key challenges and causes. So I would highlight two key challenges to increasing productivity. And one of them is a technical challenge and the other one is a human challenge. The technical challenge has to do with insufficient tooling. And in my environment, we often work on large-scale machines. Of course, people who work outside of mainstream development, for desktop or web applications or whatever, we all face these kinds of challenges in that these less common environments tend to lack tooling to the same extent that people working in more common environments have. And so we don't necessarily have debuggers or performance analysis tools that scale or provide useful feedback for floating point computations, or whatever the particular challenges that we need to face in scientific computing and high performance computing. We also lack good tools just to find relevant papers or code or libraries. We all spend a lot of time, I think, in the academic community, searching the literature for previously found ways of addressing a particular problem. But this is hard. I mean, if you know that you have some kind of equation that you need to model on a computer, for example, there's no search engine you can go in and type in your equation and it will tell you, papers or code that addresses a similar kind of thing. And this is a huge problem, I think, when we look at how we take advantage of past work in this space. The second challenge I want to highlight is a human challenge, and I'll call it insufficient forethought. So, people often, of course, want to do things in the most productive way. No one wants to waste their time. So it's important, however, to understand that there are different phases to doing development, and there is a really key role to doing research and creating prototypes, and then there's a very key role to creating production quality software. And it's important that you choose the correct tools and techniques and procedures for both of those phases. And sometimes you have to do that separately, because the right way of doing a research prototype is not necessarily the right way of creating a production application or code base that you intend to live for a long time. And you don't want to prioritize, say, the time to create the first mostly working version over other factors when you're creating something you expect to live for a long time. Whereas you might do something like that if your goal is just to create a quick prototype to see if some algorithm will work. And so the idea that you have to choose the right tools and procedures at different stages in the development and the research process is something that I have experienced as a challenge over the years. Now, I think that one thing that is very nice to see is that there is good work on all of these fronts going on right now. So on the tooling front, we see work in compilers and in tools that can scale, that have minimal overheads to do debugging, to do tuning. Like we have sanitizers now that can do instrumentation-based debugging. There's work to enable those at larger scale. There is work on automated refactoring tools. We now have groups I know at several labs who are using Clang Tidy plugins to do automated refactoring of their code. There's some work, for instance, work funded by the DARPA Muse program over the past few years on better systems for searching through code and related things. And also there's work on enabling appropriate tooling for automated code generation, from things like mathematical descriptions down to high performance implementations. And I think all of these things are going to have a key and positive impact on productivity. So thank you.
Thank you very much, Hal. Nice job. So next we have Todd Gamblin. Todd, take it away.
Okay, hi, I'm Todd. I work at Livermore, and I think I have a definition that's kind of similar to Hal's, but maybe not as rigorous. My definition of productivity was just how quickly can I go from a description to an implementation that satisfies their requirements. And maybe that violates the full life cycle that Hal mentioned, but I don't know. I think I include the life cycle in the requirements. So I guess I put in there that language was important, that it's important to have a simple and intuitive implementation of your problem, that having extrinsic non-problem related concerns is important. So if the language does a lot for you, or if the tool does a lot for you, that's good, because you don't have to think about things that that you might have tripped over if you hadn't used the tool. And then I also put, does the language meet the performance requirements? Because I could go from a description that mostly satisfies the requirements if I wrote in some really high level language. But in HPC, we care a lot about performance, and often that's like the first concern. And so I think it's important that you program in something that's also performant, and that's often a stumbling block for HPC folks. I said terseness is not always a win here. If you have something that lets you quickly go from a description to an implementation that satisfies the requirements, but nobody can reason about it or change it or tweak it, that's bad. And so having a system that's easy to think about and that makes sense is important as well. And that might make the description longer and less intuitive, but I think if it's an important thing to think about, it needs to be represented in the language. So I guess for key challenges, the thing that I deal with most is building HPC code these days. And I mean, I've dealt with it forever because it's a really slow and unproductive task, and it's no fun to build HPC stuff. There's a need for performance there, and so there's this de facto requirement to distribute as source code that I think people trip over. It's very hard still to distribute optimized binaries for HPC. Just knowing whether or not you can use some binary that's on the system with your code, or that you get from some website with your code, or that the thing is even going to work on your system is hard. There's not good tooling for that. And then there's just a huge number of platforms and environments that we have to support for HPC. So I think in the current landscape, there's like 4 CPUs and 3 GPUs that we have to care about for DOE. And that means that the application developers have an awful lot more to think about than at a company where they've probably chosen some platform that is what they're going to ship on, or what they're going to run their cloud service on, or whatever. I think the portability argument has kind of, or the portability as a concern for software development has decreased as people have moved to the cloud for most web services and things, where you can pretty much control the hardware that you run on. And I don't think HPC people have that luxury. I had in here that optimizing HPC code is hard, mainly because it's hard to share knowledge across environments. I think people have pointed out for a while that if you read HPC performance papers, they have a really short shelf life because they may be tied to the particular environment they were run in. They're probably tied to a particular machine they were run on, and they're probably tied to a particular version of the OS MPI implementation and compilers on that machine. And not a lot of that is preserved in a way that you could take the knowledge and apply it to a new performance optimization problem. And so you don't know whether the things that you learned about one system or code or input deck are good for another. And there's not a standard way to track that provenance. And so I think, if we had a way to track that kind of provenance, we could increase productivity in the performance domain a lot, because you could actually make inferences about past performance studies in a way better way than you can now. So what are we doing to address these challenges? So I work on SPAC. I would say that one of the things that we do on SPAC is we build DSLs for describing builds and software configurations. And so SPAC has 3 of them. There's a command line syntax that you can use. There's a DSL for the packages that describe, what do packages depend on, what are the constraints on how you can build them and how they can, how they work. And then there's YAML for setting up environments. And so each of those is sort of a DSL in its own way. It has to be intuitive. It has to make sense. It has to enable some developer to quickly build what they want to build, and then we try to build it so that they can extend it in new directions once they've built one thing, so that the next step is intuitive. It's not a whole other section of the documentation that you have to read. We're trying to create models of binary packages so that we can better understand compatibility and reuse. One of the things that has come out of SPAC recently is we have this library called ArchSpec that models the microarchitecture that you built for. So we're trying to come up with ways to reason about whether one binary is compatible with another. That encodes sort of the whole DAG of Intel compatibility in the world of AVX 512, as well as other architectures. And I think there's more things we could do there. And then finally, probably the biggest thing we're doing in SPAC right now is we're reworking the solver that we use to understand dependencies. And there's a number of things with that. One is we're adding full backtracking so that you can do much more inference on your software stack than you could before. And we're trying to model things like the compilers and runtime libraries and all the stuff under the hood that is usually hidden from people that really affects compatibility. So I think if you can model and understand the constraints on how you can use a piece of software, then you can go and build a tool to find good configurations. But right now, the definition of that stuff is really murky. And so we're trying to add that to the model and just make it easier for people to assemble software fast. Thanks.
Thank you, Todd. That's very nice. Thanks. Okay, our final panelist startup is Theresa, Windus. Take it away, Theresa.
Hi. Well, being the last speaker, I want to thank the organizers again, but I also wanted to say it's kind of challenging to figure out what to say when everyone else has said everything that you wanted to say. But
I apologize for that. I tried to do, I thought about doing reverse alphabetical. I'm sure you are put in this position often. I apologize.
Somebody had to be last.
That's totally okay. My maiden name was Brown, so I went from the beginning to the end, so it's okay. All right, so some of the things that I think are important for productivity definition is usually there's some concept of fast, and we've heard a couple of metrics that might sort of relate to what fast means, but hopefully, you know, the idea of some sort of quickness is part of that. You want your software to accomplish the goal that you set out. Quality is an interesting piece, right? Because ultimately, that can be defined in many different ways. It might be, did it just do the job that I needed to do right now, right? Again, maybe a short life cycle kind of thing. Or if it's a longer piece of software, is it something that I will never ever have to touch again? Maybe that's a metric for quality. Excuse me. But there's some idea of elegance maybe in there, right? Quality is kind of a fuzzy word, which you can use in many different ways. Reusability, maybe you don't need this, right? If it's a very short-term project, you need to get results very quickly, which can often be the case in academia, then maybe you don't care so much about reusability. Whereas if you're in a environment where you're building a very large piece of software, reusability may be something that you're very, very interested in having. Todd just talked about the building process, right? I can't tell you how much time my students and staff in my different projects spend trying to build stuff, especially when there's dependencies, right? So if we don't include this in, I think we've made a big mistake. Debugging, we also heard about before. Debugging can be challenging, especially if you're trying to look at software across many different platforms, or if you're running on a very large scale system, scalability becomes an issue. And then sustainability is a question of whether, or excuse me, has to do with the life cycle of the software. Do you want it to be sustainable? Maybe you do, maybe you don't. What does that mean? Well, refer back to the previous Collegeville workshop for all of that. But all of these elements, I think, in one way or another, impact what we think about productivity. And it all depends on the project you're on too. Not every project's going to have the same kind of goals for productivity as other ones. So I think we have to be careful as we're thinking about this to define it within the context of the kind of software that we want to build and what our goals are for that software. I'm not going to get into this very much, but metrics to tell you if you're doing a good job, that's really challenging because, you know, I can do very fast development, put out a bunch of lines of code that might tell me that, yeah, I'm being productive in the sense of putting out a lot of code, but maybe the quality is poor. In other words, there's a lot of bugs or the end cases aren't looked at. You know, so developing a whole group of metrics that tell you if you're doing a good job can be really challenging, something that we need to think about, again, kind of in the context of each of the different software projects that we're developing. What are the metrics that you want? And how can you tell if you're meeting those metrics, right? That's a very challenging thing to do well. So I'm going to move into some of the key challenges. You've heard quite a bit about most of these. So I will say design and documentation. When I'm developing something that needs to be around longer term, if it's not designed and there's no documentation, I personally don't consider it as being well done. You really should be spending a lot of time in design phase and trying to figure out what you need to implement before you start the implementation, or maybe in conjunction with some prototyping, as we've heard about before. Prototyping. All right, so I'm in an academic situation most of the time. I also work with a lab hat on as well. So prototyping is really important, but it's often the case that the prototype becomes the software that you use. And when that happens, that's where you can get into a lot of trouble, because a prototype really is meant to be sort of, is the idea working? Is the physics working? can I actually make this work the way I think I want it to and have it perform the way I want it to? Well, you know, if it sort of does what you want it to, then maybe it's good enough to be the software that I need. But oftentimes the answer to that is no, it's not. And you really need to sit down and refactor, rethink, redesign to make it even better. And especially if you're going to keep it around for a while, to make sure that it has some maintainability and sustainability. Roots of some of these problems are lack of time, money, education, right? If I had infinite amount of time, infinite amount of money, or infinite amount of education, I could probably do this right the first time maybe, but I don't. And if I can't do it right the first time, then it's going to take me more time to do it the second time, right? So there's sort of a trade-off between time, money, and how high of a quality code you need to be able to operate. So we're always working in this sort of idea of having these trade-offs. We heard this mentioned before that there are lack of rewards for creating really good quality software, especially in academia. The labs in the industry, I think that's less of a issue, although there's still issues there. You know, grad students don't often want to don't often want to think about making software for someone else to use. They just want to make it work for the problem that they're involved in, so that they can get that paper out, right? Now, I think this is evolving, but that's good, you know, which is great. So we're getting more rewards for doing great software development, but it's still an issue. Excuse me. Some of the couple things that we're doing is I'm involved in the Molecular Sciences Software Institute, which is an NSF funded institute. We're working to try to educate our community on standards, awareness of just the issues of productivity, and for best practices, especially in software engineering. So we're trying to help people who don't have a lot of formal training in computer science to actually get some of the education that they need. And instead of doing it in sort of a quote ad hoc way, to provide sort of a systematic training process for them. We're also looking at developing standards within MOLSI that our community can use, so that way we can enable better reuse and hopefully higher productivity because of that. And so one of the things that's related to this is domain scientific languages. So we are actually doing work on things like tensors that kind of run throughout a lot of, say, quantum mechanics, and seeing if we can find some ways to make that available to the community. On the build side, we're actually, as part of my exascale computing project for NWChemX, we're developing something called CMake PP, which tries to take CMake just one level higher in sort of a C++ object-oriented kind of manner to try to make it even easier for us to do our builds. But, you know, there's no silver bullet for builds. You know, I think that's just kind of the message, at least for now. And things that were mentioned before, like, you know, containers, SPAC, those sorts of things, those are helping, but there's still not, I would say, the standards out there that everyone knows that this is the approach to take. So it's still a very difficult landscape. And I think that'll do it for me.
Thank you very much, Theresa. Very nice things to say. You still managed to have some points to make. Thank you. So, all right, so we're going to move on now. We've had the introductions from the 6 panelists. We will lose Todd Gamblin at the, I think that's about 15 minutes, top of the hour. So, so if you have some question for him, you know, please try to get it in earlier rather than later. So what we're going to do next is...
But I'm leaving? I think it's,
say that again?
I don't think it's me.
Oh, I thought it was Todd. Oh, Rick, sorry, yeah. Thank you, sorry. Yeah, Rick has to leave in about 15 minutes. Sorry, Rick Arthur.
Had
the wrong name. Yeah, okay, sorry. So if you have a question for Rick, you know, maybe get that in sooner. So just to remind people of the protocol for the Q&A, we're gonna use Zoom chat. Just type a brief form of your question. when your question is mentioned, please unmute to ask verbally. And then if you're not asked to speak, just keep muted. We've had some nice conversation already going on the day one chat channel on Slack. Please keep that up. And then we end at 11:30 a.m. Central Time, where no more questions. So are there any questions? Okay, so let's see. So Nate, Nate Georgia is our comment analyzer. What do we got here?
Looks like Mark has a question for Todd.
Okay, very good, thank you. So go ahead, Mark.
Yeah, hi Mike, hi Todd. So I like your definition of productivity there, Todd, but it seemed to not include the size or quality of the resource used to implement. So the absolute time to completion of implementation, that kind of depends on how many developers, what their level of experience is, and so forth. So is there a way to sort of normalize that a bit with the issue of the resource?
Yeah, I mean, I think there's probably lots of ways you can normalize it. I actually, I saw Hal's definition of productivity and regretted that mine was insufficiently parameterized. So I'm open to all additional parameterizations to my definition.
Okay, thanks.
Okay, let's move on. What's the next, Nate?
It looks like Charles has a question for Theresa.
All right, very good. Charles, you want to speak?
I think you're muted, Charles.
Yeah, I think you're muted if you're speaking.
Still muted. If you turn to the camera, we could read your lips.
I could probably just read the question from the
chat. Maybe. Let me just read it quick and then. Okay, so Charles says, based on Theresa's comment, prototypes become the software. Is there terminology we can use to make people understand what level of quality a particular piece of code meets?
Yeah, I think that's a really interesting idea. I sort of have this ladder that I think of with my students and even with my staff as we're developing like our exascale computing software, but I don't think I've actually formalized any terminology. But oftentimes it comes down to, is this quick code that's not going to ever be used again? Or is this something that we're going to use pretty much in our group, but it might live a while, but it might not be, it doesn't need to be perfect. And then when we start thinking about, I like the word ecosystem, how our software fits into a bigger ecosystem, then we need to start really thinking about that higher level of quality. So I've not formalized anything, but I kind of have those ideas. I'd be interested to hear if anyone else has sort of formalized some terminology. I guess what just came to my mind is kind of this idea of enterprise software. Kind of think of that as being, top level quality. And then you think of sort of hack together code. So maybe there's the two extremes, but I don't know what you call the bits in between.
Yeah, I had the same question myself, going from prototype to production. It's a very challenging issue, I think. Any comments from other panelists on that?
Well, Sunita here, it's a very important question. We do have the NCAR project, which we will take to production as soon as the software is ready, in the debugging phase and acceleration phase. There is a sort of a workflow NCAR has in place, nothing streamlined yet, but I see that they would use what we have created in multiple projects, which are I would say, already in production. So a function that we might have accelerated could be applied to something that is already in production. So I don't quite know what would be the steps they would take to get there. But we often discuss it in our weekly phone calls, that we don't have a standardized workflow, if you like.
One thing that I'll add is that I think while it's useful to delineate work on prototypes from work on real, on the production applications, one thing that I do encourage people to think about is that the tests that you write for the prototype might very well be the real tests in the sense that, like in many other cases in software engineering, if you don't have good tests for your code, you really can't change it. And so the transition from the prototype into another form, maybe a more production quality form, is affected by the same factors. If you don't have good tests, you won't really be able to make the transition in many cases, especially if you've now built some confidence in the fact that the prototype is doing the right thing. And so I think that it's important to think about that transition, and part of going from the prototype into the real code is to make sure that you have tests that you can also transition.
Thanks, Al. Nate, it looks like we may have a couple questions for Rick Arthur, who has to leave in a few minutes. Maybe we could hoist those to the top.
Yep, looks like Fan has a question for Rick as well as David.
Okay, so I see about the current practice from industry to deal with risks, ecosystem, health, sustainability. So there's a side project I did with a bunch of our legal team on the spectrum of open source licenses, and some of them are somewhat hostile to industry. So we titled it Apache or Better, and kind of had a graded scale and a heat map of what some of the implications are. So just in terms of indemnities and freedom to commercialize, that is a factor in some of the ecosystem as we assess what we can actually take advantage of. The other is having a dependency on something that may go bankrupt, or the grad students move on and such. And we've had arrangements there where we have source code put into an escrow, where if one party disappears, we can just take the source, even if we were getting a binary or some abstracted version of it in the prior use. This way we don't have that persistent reliance on a live team to move forward. But that does put an obligation on us to then reestablish that knowledge base and experience with the code. And then from David, examples of external package library that was added to a production code. How is that done? So I am aggressively trying to do this with Mike right now to get some of the ECP libraries into a internal solver that we have. And this is, it already uses PETSI. So that is a gateway that hopefully is going to be an enabler as such. The problem ends up being that the regression tests that we rely upon, especially if we have a history of certified work, there are concerns to the point again about certification, that as you make these kinds of changes, particularly things that can change the numerics, we will have to retroactively requalify everything we have ever done with the changed code, which represents not only a significant cost, but also now risk as we need to explain any inconsistencies that, that may expose. So imagine doing this for tens of thousands of aircraft engines, you know, over, you know, prior decades. So there are certainly deterrents to that, and our best opportunities are when we can have a clean break and move forward. And the code that we're looking at right now is in fact an entirely new code that we're moving forward, and that gives us an opportunity. Did I answer those questions?
Yeah, thank you, Rick. That was very good.
Great. Thanks very much, Rick.
Any other panelist response to that particular theme? I
see there's a question for me and perhaps a question for Theresa, which follows. But to Rick's question, and he's actually inviting everyone, every panelist here, he's asked us about the awareness and how we can kind of improve the awareness at the ecosystem level. And I think Theresa actually mentioned this this notion in her opening remarks as well, kind of. So there must be some ways that we haven't thought about yet, and maybe you are more familiar with, but from my work with James, and we thought about, so the first thing is how to make the environment of each software components, its dependencies, all the
I think we may have lost the fan a bit.
Really developers of the single software component. Excuse me?
Yeah, we lost you momentarily. Go ahead, okay. Keep going.
Yes, so where was I?
You left off at developers, how the developers of and then your face froze.
Oh, okay. Thanks. So we were talking about to visualize the dependency structures of scientific software components so that developers might be more aware of the environment that they need to deal with. So that would be one way, but I don't know if there were other ongoing approaches that perhaps, I don't know, for larger scale software projects, how do you inform everyone in the team about the interrelated projects and the possible risks that emerge from them.
Thank you, Fan. Let's see, Nate, do we have other questions that have come up?
Yeah, Anshu has asked a follow-up question for Theresa, if Anshu would like to voice his question or her question.
So my question, it isn't a question so much as a statement that in scientific software, I don't think there is a thing, at least in application scientific software, I don't think there is something that you can differentiate from an ongoing high quality prototype, because it never gets into a production mode where you're not continuously changing it based upon ongoing research in numerical methods, applied math, and scientific domain, et cetera, et cetera. So really a question might be, how do we maintain a high quality, and what are the constraints for a high quality on long-lived prototype?
Anshu, I think this is a great point. I guess the way I think about these things now is that you have some high-level scaffolding that oftentimes is the piece that holds everything together. And you don't want that to be in prototype constantly changing all the time. It will have to change sometimes, but you hope that you can do a lot of modular work to make sure that it's the modules that are in prototype, and maybe you're adding new prototypes as you go along. That scaffolding will eventually kind of break once the physics gets to be quite large. At least that's what usually happens, because you haven't thought about all of the possible ways of using that scaffolding or your physics or whatever. So I guess the way I still think about it is design as well as you can, being aware of all those dependencies that that Fawn was talking about, making sure that you're aware of the larger ecosystem as much as you can be as you're evolving your software. But you know, it really kind of does come down to having a lot of maintenance and someone who's dealing with those issues on a regular basis. And for us, we try to have those team discussions, so that way there's more than one person that's you know, the gatekeeper. You want to have everyone sort of at least understand conceptually what your design is and how the prototype's going to evolve over time. So I think this is a really good question. It's not something I will say we've solved. I think it's just something that we try our best to make sure that we're aware of and keep evolving our software and thinking as the code is moving forward.
Thank you. Yes, that's exactly how we deal with this situation too.
That's good to hear.
Nate, do we have another question?
Looks like we just got one from Ronnie.
Great. Ronnie, you want to speak to your question?
Yeah, sure. Hi, everybody. This is Ronnie from ORNL. So thanks to all the panelists, but Theresa kind of pointed out, I'm not trying to single her out, but she kind of pointed out that it's challenging to quantify productivity. And that's a challenge that we see in papers and conferences as well. Let me turn off the music in the background, my bad. But so we work with a lot of, so I'm a computer scientist, but we work with a lot of domain scientists and application developers at the facility. But in CS conferences or even in communities as well, we don't get to see productivity being defined as the science produced over the input, which is the coding effort that's going in. Is this something that, as a panelist, you guys feel that the CS community is not accepting this from the people that are submitting papers and stuff, or is it like papers are not even being submitted with this into account? So
thank you, Ronnie. If I may chime in, Sunita here. So yeah, we constantly think about this when we write, you know, papers in my group, because there is research and development, right? And when you submit this to conferences, sometimes they do get pushed back saying there is more development, less research, or there is more research and, you know, there is less development narrative, basically. To that end, I should point out that there are the state of the practice tracks in IPDPS, for example. I believe this year would be the second or the third one in 2021. And SC has a state of the practice or something similar, a track. So I would like more of these tracks in premier conferences where you can actually talk about, you know, narrate in your paper what were the productivity challenges, what were the coding challenges, and how do you overcome it? Because unless we describe the process, it's difficult to actually, you know, discuss what were the coding challenges. One such effort we had was this mini sleep code from Oak Ridge again, which was a mini code of de novo application, where we published this in PASC. We have a journal in CPC, wonderful. But the paper predominantly talks about the algorithm and the algorithm restructuring, very little about, you know, what were the coding challenges, but it was about a year's effort. And we haven't talked about that anywhere because of, you know, lack of appropriate venue. So thank you for asking, but I think there should be such venues. And I see some, I see Dan has posted on the chat channel as well.
So on the topic of science per effort, I think that's a really hard, I think that's harder to quantify maybe than productivity. Because I mean, I guess I've seen like our Coral benchmarks that we put together with Oak Ridge and Argonne, and they have figures of merit where they say, you know, we did this many molecular interactions per unit time, and so it's like a physics-based performance metric. But but that's not science, right? Like that's just how many interactions you're simulating. It's a physical property, and I guess like I don't know that science per coding effort is the greatest metric, because like if you measure science in terms of number of papers, you could have a really high impact paper that took not a lot of coding, and you could have a really low impact paper that took tons of coding, or you could have anything in between in that space. And so I guess I don't know that I want to see a bunch of papers that say I wrote 2 lines of code and got this awesome science result. Like I guess I feel like that's not, I don't know how useful that is. And I think like if you optimized for that metric, you would not do a lot of things that are worth doing. So I worry about that.
I guess a quick follow up on this. When I said science, I actually meant the delta of, let's say, from where you were. Let's say your funding agency started in 2019, and then 2020, the science that changed from the time you started that project to the time in 2020, like a 1 year time frame, and what changed in the actual code base to get a different product, like different. I understand it's a challenging thing to quantify, but I'm saying that people are not even trying. That's what my point is. Coral 2, yes, Coral, we do a different benchmark, sure, and that is all science specific, because the figure of merits are something that the science teams are told to generate, not us, us as in like OLCF as well. So that's kind of the point. But I understand it's a challenging thing, but I'm saying that is there a reason why we are not trying?
And maybe I could just add one thing, which I think you were actually saying, Todd, was that kind of relates to that, is that the impact is actually over time as well, right? Because you can get something out quick that might have some short-term impact, but maybe not a really long sustained impact. Sometimes things you don't see their impact for 5 or 6 years, right? So on the science side. So it can be really challenging to make, I mean, I'm not saying we shouldn't think about it. It's just very challenging.
Well, and then how do you, the other thing is for some software, like there's no direct scientific impact. There's only indirect scientific impact. So if you're building some deep dependency that everyone uses, you probably had a pretty big impact because you saved a lot of people a lot of time. But you don't get the credit for the science, right? The teams that did the science do that. And so, I mean, I think that makes it even harder to measure in an ecosystem if we're talking about software ecosystems where, everyone is relying on, hundreds of other packages. And I think that has to be taken into account somehow.
Right. And especially if you're building this chain, like you're saying, of software, where the science paper might only acknowledge the top level software, it never digs down and gives the references to all of the other bits, right?
Yeah, so, exactly.
Yeah.
Like GCC has probably produced an awful lot of science per effort, but I don't think anyone would say thanks GCC in their paper.
Very nice. Okay, Nate, what's next? We've had some nice chat here.
Yep. Ben has a question for Theresa.
Yeah. Okay, Ben, go ahead.
Yes, thank you. So I was wondering if you had any ideas about what some reward systems might be, because you mentioned lack of rewards as an issue for productivity. And I guess, is there some sort of equivalent to a peer-reviewed publication where, normally you publish a peer-reviewed article and you get citations, and I guess in software, you sometimes try to shoehorn the software into that system where you publish a little paper based on the software and ask any of your users to cite your paper in their work if they use your software, which, I don't know, might not be the best metric. So what are your thoughts on that? And I also saw that there's a few people in the Zoom chat that offered some responses as well.
Yeah, I actually think I'd like to deflect that to people who were answering it in the Zoom chat, because I think they had better ideas than probably I do, and have probably thought more deeply about this reward structure. I can say that in my group, we try really hard to make sure that everyone realizes that the reward is that may not be direct to you, but it might be indirect to other people. You can make other people happy by doing good quality software. And, you know, that way it will help the group as a whole, right? And you do get a reputation if you're really good at making good software. People do kind of figure this out. But, you know, that's a little less tangible. So I'm going to deflect now to those people who were writing in the chat, because I think there's some good answers there.
I think Daniel Katz and James, and then there's, oh yeah, James Howison also responded that I could see. Thank you.
James or Daniel, you feel free to speak up if you want.
Hey Mike. Sorry, this is Dan. I guess I can turn my camera on, see if that works. So I think there's a lot of different options here. There are a number of different journals that will accept software and review it in different ways. Most of these are based on what our OpenSci originally practiced in terms of having a good set of review criteria for the software. JOS is probably the lightest weight version of this, where you write something like 1,000 words, and then the review is mostly of the software and the repository and the issues and documentation, and then also of that extra stuff you wrote. There's other things kind of on the other side, where you write a full paper and mostly it's the paper that's reviewed and not really the software repository. So I think there's a lot of different options here if that's what you're interested in. There's also the fact about trying to think about what people are doing and make sure that they have a career path that matches what they're doing, and that their group supports that, and their management has good metrics for promoting them and hiring them, and things like that, which are probably better in labs and industry than in universities at this point. But we're trying to use the RSE movement, the Research Software Engineer movement, which you can find out more about at USRSE, us-rse.org, if you're interested in this as well.
Cool. So this is James Howison. So yeah, the key thing here. Oh, I had a post-it note on my camera. The key thing here is sort of twofold. One is publications, but then with that is deciding how you want to be mentioned in the literature. Right. So if you want to be mentioned in a particular way so that you can then keep track of that, that is something that projects don't necessarily kind of think about. Right. So I think that when scientific software projects are picking a license, setting up development venues, deciding on their continuous improvement, continuous testing environments, they should also be saying, how do we want to be mentioned in the literature, and making a clear request for that. So once that's decided, then there are emerging ways of doing that, such as a citation file at the top level of a repository, and some other machine readable approaches. And our poster later today will focus on citas.org, which is an attempt to just write a very simple specialized search engine to find those requests, so that users can drop in the name of your piece of software and know how you want to be mentioned. And of course, the way you want to be mentioned might change over time, right? If you write a new paper or new developers come on and you want to make sure they're getting the kudos that matters. The other thing is, and I'll post a link to this in Slack, but at a Dagstuhl a couple of years ago, there was sort of a list of things we can do to bring more rewards to good software work. And these are, for example, when we're reviewers of papers, making it clear that people should be mentioning the software in particular ways, or when we're reviewing grant panels, asking questions about the software development work, and also working with the personnel branches within our various institutions, so universities that will be pushing up to tenure level policies and making sure that software contributions are being counted there. Now, the one that I don't have a great deal of insight in, and I'd love more insight in, is how do we encourage and reward contributions to other people's projects, right? When we take an ecosystem perspective, we've got to start to think about pushing upstream. And that one's a nut that I think is really difficult, but I'd love to hear thoughts on that.
Thank you, James. Let's move on. I think we have a few more questions. Nate, what's the next one?
Vadim has 2 questions.
Okay, Vadim, you want to voice your questions?
Yes, so I'll skip the first one. I think it's more or less trivial. And my second question is, did you ever have a feeling that your project became too large to be handled efficiently? And can you somehow quantify that cap on the project size, where it became just, you know, just the size problem became an issue on its own?
I think that was when I had to start installing email filters. That was my break. There was a day when I was trying to participate in a meeting at Los Alamos, and I couldn't stop checking my inbox because I was getting emails like way too frequently, and I could not deal with all of them, and it really stressed me out. And that's when I felt like the project was too big to keep track of.
I think it's a good practical criterion. Anybody else?
One thing that I will mention quickly is, and this has come from my experience dealing with the LLVM project, which is a fairly large project, is that as a project grows, you end up needing to put in more structure on the management side to keep things sane.
Yep.
So when a project is small, you can often just have a small group of developers that can kind of you know, proceed by consensus, which can almost always be reached because it's a small group and everyone knows each other and so on. And as the project gets larger, you know, you end up needing to have defined roles for people and defined procedures to escalate and resolve disagreements and so on. And that's important to realize as well.
Thank you.
To chime in, I definitely do not have such large size projects, but thinking out loud, the car project that Ronnie and I on this channel are on, sometimes I look at it from a priority standpoint. You know, so what is so FOM, right, the figure of metric, that's top priority for car projects, for example. But if you take the science of the code itself, there are so many things that you could do to use frontier kind of a system, upcoming system. So you could improve the science. You could, you know, recreate algorithms. You could create new parallel algorithms. But sometimes what helps me is to go back to Oak Ridge and tell them, okay, what is the top priority? Then you organize your to-do items based on the priorities. Obviously, the several aspects of the project gets lower down the list. You can still get to it, but you have the top 2-3 items to get through. So that kind of a reorganization of what needs to be done has helped me with, you know, car type of projects.
I also want to chime in a little bit. It just sounds to me that all your comments come from mostly the work side or the human resource management side or the real manager work involved in the software project, but less about the technical aspect that you need to manage. And perhaps it's just because the technical aspect is harder to perceive, though it has its own trouble. But just because I saw Vadim's question, actually the first question as well, is kind of related to that. So I'm offering some statistics that I know, because Vadim asked about kind of the optimize the size of software development team. So based on something I know, so there are some study on teamwork using patent data that they found that a team of 5 to 8 is the most productive. And after 8, the productivity curve starts to drop. But that's hidden data, not necessarily software work. And as far as I know, so Microsoft, the software development team, because they have a good implementation of the DevOps practice, so their team is hybrid, a software engineer and IT operation person and product manager are all involved, and each team is like from 3 to 5. However, after the machine learning becomes a important part of their software engineering work, that increases the burden of the software engineering work, and their team size becomes to expand. And now they're like also more than 5, they have more data scientists involved in the team. So I think so. First, the technical aspects that how much technical data you can manage might be a consideration for an ideal team size and when you're planning for your teamwork. And the second thing is based on the applications that you're building, whether you need to involve different roles into your teamwork, that might be also a consideration criteria when you're planning for development teamwork.
May I ask a follow-up? You mentioned the data scientists. Are they helping developers to deal with the software project, or they are just subject specialists that write their own part of the project?
I think it depends on the actual work involved, because if you're developing a machine learning oriented application, I think necessarily the data scientist needs to involve into the actual practice. But if your actual work structure is you intentionally want to separate the data scientists and the software engineering part, and there are some practices pursuing that because they think in machine learning intensive development, there's a lot of math there. So to split the two processes, especially when your project comes to a certain scale, would facilitate the productivity, let's say. So then it will be good that to keep them separate and the data scientists only provide insights to the software engineering side. But in the meantime, you need to make sure your team design, have some cross-functional opportunities for both the data scientists and the software engineers on your side.
Thank you.
Any more comments on that theme? Otherwise, let's move on. Nate, what do we have next? Looks like we have at least one more.
Yep, we had a question from Mark Miller a while back, if he would still like to ask that.
Okay.
Gee, I don't actually remember that question, but since it's following on the questions about project size, I'll just ask the one I just put in. The speakers before Fan Du mentioned size in the context, it sounded to me like number of users. Todd, your comments about email it sounded like the notions of size being expressed there had more to do with how many people were using it rather than either how big the problem was that was being solved with the software or how big the software project itself was. And so I just wanted to circle back. Is my impression correct, or did I misunderstand you?
I think it's both, but yeah, I think that's an accurate summary.
Okay, because at the end of the day, you want to have more users. But the problem of supporting them, of course, scales with the number of them, and that's a completely different challenge than obviously. I think the question that Vadim was asking about the size of the actual software project.
Yeah, and I mean the size of I don't know. At least for me, the size of the project is the ideal size of the project is always bigger. Because we always need more people to do things. And I mean, we can do that either by hiring people or by just, delegating to members of the community and having them, take responsibility for certain parts of the maintenance. And I mean, to some extent, we kind of passively do that because they're just people who step up and do lots of useful things, which is great. But I mean, I think we polled some of the software teams at Livermore about like lines of code to developer and how much code they actually have to maintain. And for scientific software, the number of developers per line of code is way more, is way developers per line of code is way less than industry. Like I think for a similarly sized code in industry, you would have a lot more people maintaining the software. I guess for me, it's really a sustainability. When do I feel about email and like nobody else is gonna, so I think it's, it's the ratio of those two things. How many users do you have? How much effort are they doing? How many problems does each user have? And then how many developers do you have to deal with that?
Thank you, Todd. Nate, what else do we have?
We had some comments from Reed, Chuck, and Ronnie. If any of those lead into questions for the panelists.
Yeah, maybe Chuck, do you want to, we haven't heard from you as far as I know.
Sure. Hi, thanks. Yeah, I was. My comment was with regards to back on prototype versus production. So at being at Kitware, we are industry, but we operate in the kind of government contracting space, and the nature of the software being prototype and production often ends up a function of the funding source on where it came from. So, for instance, if it's like a, phase one SBIR or like a phase one DARPA program or something like that, what is getting funded is almost by design to be a prototype. And, what we've, and we're certainly, we've, kind of developed a culture within the company of, that, explicitly as part of any ongoing effort or a phase two effort that, there really needs to be an overall culture within the team to have that move to a production type software and everything that goes along with that. Because there's often a temptation for that focus to be on just, doing more science, more features, and et cetera. But, unless you're really just intending it to be like single purpose one-off thing, that doesn't really work, which I think everybody kind of knows. But a big part of that is really a culture within a team, not just the things that you do.
Thanks, Chuck. Any comments from the panel on that? Thanks. That's a nice perspective. Let's see. So I think you mentioned, Nate, that we have a Reed, right? And then Ronnie, and then I see Ross. And maybe we'll do those as the last three. Try to keep them, brief Q&A, and then we'll wrap up with a few notes about the discussion. So Reed, are you what you want to make your statement? Question?
I can. Which statement are we talking about?
I'm sorry. I thought, Nate, that you had.
I did. But yeah, there was a discussion on the side about the need to publish in venues that really care about productivity concerns, right? It's something I can speak to on the panel on Wednesday, but I've been in many, I go to software engineering conferences all the time, and I rarely see scientific software folks there. The conversation's always dominated by Facebook, by Google, by other people. And it's not that they're more important, it's just that they show up and they get all the attention and all the researchers working on their problems, but not our problems, right? So I'm curious about like if there's an appetite for trying to reach out to these other communities. How do we build bridges, right?
Yeah, very good. Any comments, questions on that? Comments from the panelists?
I mean, I'll just say that interest. Oh, go ahead, Hal.
Oh, thanks. I was just going to say that I think there are two things I'll say. So one is, I think we are building bridges in areas where we have directly overlapping interests. And, for instance, we work on productivity enhancements within the LLVM project, and so does Google. And, there are areas where we collaborate there, and that's really important. The other thing I'll say is that there are some areas where our interests are aligned at a high level, but in terms of particular technical needs are divergent. And so I think in those cases, we really do need to learn from what they're doing, but sometimes, just for technical reasons, whether it's a focus on differences in programming languages or libraries or anything else, we'll need to learn from what they're doing and then make sure that we have investment in tooling that meets our needs. Sorry, Theresa, go ahead.
Oh, I was just going to add that I think those bridges need to be built both ways, right? There's a lot of scientific conferences where we're starting to bring in more computer science people who think a lot more deeply about the development and how to do that well. And I think exposing the science community to those, you know, to the broader spectrum of issues is really important. So I think it works both ways, right? And but I think those bridges need to continue to be built.
To add on to Theresa, I think the RSC component, and several on the Zoom call would, you know, or all of you could relate to this, research software engineering. That's the bridge, right? The domain scientists and the computational scientists, the more they work together, I think together we can build better science as well as better software. I'm saying this from the standpoint of most of my projects are applied HPC. 2 NSF projects are traditional HPC, but the applied HPC, I can clearly say how much of a gap there is between taking a science code and moving this to a bigger platform. There is a lot of dialogue that is needed between the domain scientist and the computer scientist, and it is not a one phone call. It takes several meetings to understand the physics before we go to a corner and apply them for a hardware of, you know, both choices, both the parties' choices. So RSC, build more RSCs.
Okay. I think out of respect for time, if we can, the questions that are in the chat, perhaps we can have those answered by the panelists or others in the chat. And let me just put up the last slide for this afternoon. Okay. So, so we're wrapping up now. We have about an hour. Please, you know, continue to have conversations in Slack. I see a lot of healthy exchange back and forth. This is great. Then please sign in, you know, promptly at 12:30. It'll be a new Zoom link. So if you go to the tinyurl.com/collegeville2020 URL, or there are lots of ways to get to it. But if you have questions, put it in the chat, Slack chat, and we'll direct you. But please go ahead and sign in about an hour, and then we'll do the experiment of a random breakout room assignments. So we will not meet again as a plenary group until tomorrow during, you know, the second day panel. And so, as always, you know, Slack is our backbone for conversation. So any questions, comments you have there. When it comes to the posters and tea times, as I mentioned, there will be an independent Zoom link for each panel or each poster and each tea time. So, you know, log into that particular Zoom session to participate in that conversation, and you can drop in at any time. Just like posters and tea time, you know, posters are modeled after a kind of poster session where you walk around with a snack or a drink and you chat with people as they're available. Tea times are meant to model, you know, small informal discussions that occur in a social event, so that you can, again, drop in, you know, in the middle of a conversation, try to catch up a bit, add your comments, and then move on to the next discussion. And we have 6 of them today, so there's plenty of opportunity for you to mix in and get to know some of your colleagues, at least in this virtual setting. So any last minute comments or questions before we sign off?
I actually have one. So for the poster and the tea time session, is there an expected time limit for that, or it's encouraged that we stay there so people can, you know, switch over different places they like?
Yeah. So if possible, it'd be great if you could be there for your 90-minute session. You know, maybe you tag team with someone else who understands the background associated with your poster. Again, very much like if you were at a poster session and your job was to, you know, to be there present, so when someone arrives. I guess, you know, if you have more than one device, you probably could, you know, be there for your own poster session on one device and then sign in for another tea time or another poster on a different device. And then, you know, if someone's not there, you know, to ask you questions or converse with you during your time, you could then maybe pay attention to the other one. Just an idea. This is all, you know, a big experiment that we're trying to, you know, continue to learn and grow as we go along. Does that help?
Yes, thanks for tips.
Sure, sure, very good. Okay, so then we start up again at 12:30 U.S. Central Daylight Savings Time, and look forward to seeing you on the other end of the break.